Picture this. You're in the final round of an interview. The last question drops. Explain how you would design a database system that is foolproof, meets our constraints, and can scale from 0 to 100 million users. Suddenly, metrics like latency, throughput, read, write cost, and error rate are on the table. Do you know how to answer that? If the answer is no, you're in the perfect place. Because in this video, we're going to break it all down, starting from the absolute basics. What are the prerequisites? You should at least know what a database is and why we need one. If you can write simple SQL, create a table, and name a few database types, relational, key value, document, you're ready. This video tells you each step that takes a simple table to a distributed system that survive real-world scale. This is precisely the guide you need to move from beginner to someone who can design systems at scale. Scaling isn't a single leap. It's a sequence of trade-offs. Think of growth in stages. At a very small user count or MVP stage, correctness and iteration matter the most. So, simplicity wins. But as users grow, latency and throughput become visible. And once at a global scale, operational complexity explodes, and this requires some big changes. Let's be blunt. One big relational schema will break in predictable ways as you scale. Here are the core failure modes. Huge tables mean expensive scans and slow index maintenance. As rows pile up, even simple queries start dragging because the database has to churn through gigabytes of data just to answer basic requests. High write rates cause contention. Transactions block each other. When too many concurrent updates hit the same rows, locks pile up and throughput collapses into a queue of waiting operations. What happens when one part of the database receives far more traffic than others? It is called a hotspot. A single popular key like one celebrity's profile or a trending hashtag can overwhelm it while the rest of the system sits idle. As tables grow, multi-table joins explode in cost, forcing the database to shuffle massive intermediate results and hammer CPU and memory. Monolithic datasets make restores slow and risky. A single corrupted snapshot or failed restore can take hours to recover, leaving the entire application unavailable instead of just a small slice. But how do we measure if our system is good enough? What are the metrics? Latency is the time a user waits for a response. When working with databases, we measure it with percentiles to see typical and tail user experiences. This is the primary user-facing performance metric. P50 tells you the experience most users see, and P99 exposes the true tail where 1 in 100 users hits the slowest, most painful responses. How many requests and queries per second? These are signals for incoming load on the database. And just a reminder, measuring these metrics isn't limited to database only. These can actually drive business decisions. For example, tracking aggregate and per endpoint rates can help figuring out user hotspots and thus help in better capacity planning for the business. You also measure the fraction of failed requests. What happens when error rate and tail latency spike together spontaneously? Remember, for a foolproof system, alert on combined signals. This is the amount of data that can be processed in given time. This is basic but necessary. Fast growth is only good when you can handle it, not when it breaks your bank for storage costs. This is how you would rate engineering design and set business-aligned SLOs. Given all this, alerts should be based on symptoms, not raw metrics. Now let's suppose your product stops being a prototype and becomes a real system. You still want simplicity, but you must be deliberate. Good schemas, the right indexes, and sane operational defaults will save you weeks of firefighting later. Let's take a deep dive into what's next. This is supposed to be done right when the database is being structured. Before you optimize, measure. Find the slowest queries by frequency and by cost. Prioritize the ones that are both frequent and expensive. Those are going to be your biggest wins. Full table scans are fine for tiny datasets, but on millions of rows, they become outages. That is where indexing comes in. Take Postgres as an example. In Postgres, the data of the table is stored in form of pages, which are 8 KB by default and are stored in heap. If the table has a primary key, Postgres automatically builds a B tree index on it. That means whenever you query by the primary key, the database doesn't scan the whole heap. It jumps straight to the right page using the index. A full table scan means Postgres reads every page sequentially from disk into memory, then checks each row. That's why scans can be expensive on large tables. You're touching all pages whether you need them or not. But remember, index is speed reads but add write cost. Every insert, update, and delete must change each relevant index. So write throughput and storage increase with every index you add. This is why you should index based on query patterns, not indiscriminately. This brings me to a schema design principle. Normalization is a set of rules that split data into related tables to eliminate redundancy and maintain a single source of truth. The practical benefits are strong data integrity, simpler updates, and predictable transactional behavior. Normalized schemas reduce update anomalies because each fact is stored once. Use normalization when you need ACID correctness, frequent writes, or complex transactional workflows. Whereas denormalization intentionally duplicates or pre-joins data to reduce runtime joins and speed reads. Techniques include adding redundant columns, summary tables, materialized views, and pre-aggregations. Denormalization is appropriate for read-heavy endpoints, analytics, and low-latency user-facing queries where the cost of joins is unacceptable. Designing a good schema is based on mitigating some trade-offs. Some key considerations should be read versus write ratio, query patterns, latency, storage cost, operational complexity. If writes dominate and consistency matters, favor normalization. If reads dominate and joins cause latency, consider targeted denormalization. One is best for write-heavy and OLTP applications at the cost of more joins and complex queries, while the other one can be utilized for read-heavy endpoints and analytics at the cost of extra storage and update complexity. For example, when some read-heavy hotspots found, a denormalized replica of the table can be kept. Let's discuss about some optimizing strategies, caching and replicas in more detail. If some value on an application is requested frequently, for example, dashboards loading the same metrics or APIs serving repeated lookups, you can store it in a fast cache like Redis and serve it directly from memory rather than a trip to the DB every single time. Although caching can reduce latency and database load, there is one trade-off, and that being consistency. Once you cache data, you must manage staleness, invalidation, and expiration. Let's discuss some caching strategies. Here, application is responsible for the cache logic. Here's the flow. Whenever a request comes, the application looks into the cache. If the data is available, it is simply returned. But if it's not, then the application retrieves the data from the application and returns it and stores it in the cache for future usage. This is called lazy loading. Read through. Here, the cache layer is positioned between the application and the database. Whenever the data requests come, the application goes to the cache first. If the requested data is found, simply return it. Otherwise, the cache fetches the data from the database and then returns it to the application. The cache layer is responsible for fetching data from the database. Here, every write operation happens on the database and the cache at the same time. This keeps cache fresh and improves read consistency, but it slows down write operations because you're writing data at two places, thus double time. Why use it then? Think of applications where read after write consistency matters more than raw write speed. What about a case where the application writes the data to the cache at first and then it written to the database? This is write-back caching. It ensures data is always present in the cache. But what happens if the cache layer fails? You end up with the risk of complete data loss and inconsistency between the cache and database. Write around. Lastly, write around is where you combine read-through and cache aside strategies. The application always writes the data into the database and reads data from the cache. If there's a cache miss, the data is fetched from the database and then stored in the cache for future reads. This strategy works best when data is rarely updated and read in more often. But in system design, caching is rarely a hard problem. Maintaining the state of application by invalidating cache is harder. Read replicas. Once reads become heavy enough, caching alone is not enough. That is when you add a read replica. It's a copy of the primary database that accepts read traffic while the primary continues handling writes. This instantly increases read throughput. Replication lets you scale reads without scaling writes at the same rate. It also improves resilience because a replica can be promoted if the primary dies. But it introduces lag, and lag means users may receive older data than what was just written. Now, as an application and user count grows, so will the size of database. One option would be to simply upscale vertically. That is more CPU, more RAM, faster disks. It's the fastest way to get immediate capacity for CPU-bound or memory-bound workloads. And it keeps architecture simple because you don't change application logic. But vertical scale is simply not feasible because of single node failure risk and the sheer expense at high tiers. That is where partitioning comes. It is splitting a large table into smaller and independent pieces inside the same database instance so queries and maintenance operate on subsets of data. There are different ways to partition a database, but partitioning also changes your maintenance model, and therefore two things must be taken care of: query routing and cross-partition queries. The application or a routing proxy must map incoming queries to the correct partition. You also need to detect hotkeys to avoid localized bottlenecks. The goal is always the same: make one massive traffic spike look like many smaller, manageable requests. Sharding is the next step after partitioning, but now the pieces are no longer just internal table segments. They live on different nodes, often different machines, and sometimes different data centers. Instead of one database handling everything, each shard owns a slice of the data and behaves like a smaller database in a larger distributed system. This is how you move from a big database to a database fleet. It means horizontally splitting data across multiple independent database nodes so no single machine has to carry the entire load. Each shard stores only a subset of rows, and the application or routing layer decides which shard should receive a given read or write. This is the point where the database stops being just a database and becomes a distributed platform. You now need shard maps, failover procedures, health checks, migration tools, traffic routing logic, and constant monitoring of skew and latency. Partitioning was about splitting data inside one system. Sharding was about splitting responsibility across many systems. And now comes the hard truth. Distributed systems do not remove trade-offs. They manage them. They trade single node simplicity for horizontal scale. They trade perfect consistency for availability under failure, and they trade easy debugging for survival at high load. That is why performance engineering is not about making one query faster in isolation. It is about making the entire system behave predictably when 10,000 users hit it at once, or when a node dies, when a shard becomes hot. Take an example. Writing 100 events together is often cheaper than writing them individually. The trade-off is that bigger batches can increase latency for the first item in the group and make failures harder to isolate. So, what is performance engineering in a distributed database? It is the art of balancing opposing forces, and therefore, a great distributed database system is not one that avoids trade-offs. It is one that makes the right trade-off for the workload, the product, and the failure mode it is most likely to face.